When the world went to war in 1939, military planners believed they understood what modern combat would demand. They had studied the lessons of the Great War, refined their doctrines, and built their arsenals accordingly. What they had not prepared for was how quickly those assumptions would collapse. Within months, armies were facing problems no one had planned for. Aircraft were too heavy to lift off from short or damaged runways. Tanks became trapped in mud and hedgerows. Submarines were sinking convoys faster than ships could be built. Beaches were defended by obstacles no landing craft could cross. In every theater of the war, commanders ran into situations where the correct solutions simply did not exist. What followed was not careful research or long-term development. It was improvisation under fire. Engineers and soldiers took whatever materials they had, combined them in ways that seemed reckless or absurd, and hoped the result would work long enough to keep them alive. Today, we are counting down 12 desperate World War II inventions that actually worked. These were not elegant solutions. They were gambles born from necessity. And by the time we reach number 1, you will see how desperation led to one of the most ambitious engineering triumphs in military history. At number 12, we begin with a problem that appeared over runways from North Africa to the Pacific. Aircraft were growing heavier, loaded with fuel, bombs, and armor far beyond what their engines were designed to lift. On short airstrips or in hot climates where air density dropped, pilots faced a brutal choice: strip away weapons and fuel, or risk crashing on takeoff. Neither option was acceptable when missions demanded both range and firepower. The solution came not from redesigning engines or airframes, but from something far more direct. Engineers strapped rockets to the aircraft itself. Rocket-assisted takeoff systems looked crude and dangerous from the start. Solid fuel rockets were bolted beneath wings or fuselages, then ignited during the takeoff roll to provide a violent burst of thrust lasting only a few seconds. On paper, the idea was simple. In reality, it was terrifying. Early tests confirmed every fear. Rockets misfired, burned unevenly, or exploded outright. Aircraft veered off runways or pitched violently under asymmetric thrust. Pilots reported flames tearing past their cockpits and shockwaves rattling the entire airframe. More than once, the system seemed more likely to kill its crew than save it. But refinement came quickly. American, British, and German engineers improved igniters, standardized rocket bottles, and developed predictable burn times. Pilots learned exactly when to fire them, igniting the rockets only as the aircraft reached critical speed. In combat, the system worked. Heavily loaded bombers lifted off from Pacific Island runways that would have been unusable otherwise. German night fighters carrying radar equipment and heavy cannon climbed faster to intercept Allied bomber streams. The rockets burned out, detached, and fell away as the aircraft continued on their missions. It was not elegant, it was not safe, but it gave overloaded aircraft the narrow margin they needed to survive takeoff when every pound mattered. That was enough. Before we continue, if you enjoy history told through real problems and real solutions, consider subscribing. New videos like this are released regularly, and it helps ensure this kind of long-form history keeps getting made. Number 11 takes us to the Eastern Front in the final years of the war, where German armored units faced a problem that no amount of industrial planning could solve. Tanks were being destroyed faster than factories could replace them. Allied air power dominated the skies, and anti-tank weapons had grown powerful enough to punch through armor that once seemed untouchable. Germany needed its remaining tanks to survive longer. Steel was scarce. Production facilities were being bombed into rubble. Precision manufacturing had collapsed. The solution that emerged was as crude as it was desperate. Crews began coating their tanks with concrete. On paper, the idea made no sense. Concrete added weight, slowed movement, and strained engines and suspensions that were already failing. Any trained engineer would have rejected it outright, but the alternative was watching armor split open under the first shape charge hit. The improvisation spread rapidly. Panzer crews mixed concrete from whatever materials they could find, applying it in thick, uneven layers over vulnerable areas. Wire mesh and scrap metal were embedded to hold the coating in place. The results looked crude, cracked easily, and turned tanks into rolling slabs of rubble. Yet it worked often enough to matter. Concrete disrupted the focused jet produced by shaped charge warheads, absorbing energy before it could penetrate the steel beneath. It was not reliable protection, but it was sometimes just enough to save the crew inside. By the final months of the war, tanks covered in improvised concrete armor were a common sight on collapsing front lines. It was an open admission that the conflict had moved beyond engineered solutions and into pure survival. For the men inside those vehicles, survival was the only metric that mattered. Number 10 brings us to Normandy in June of 1944, where Allied armored units crashed into a landscape that turned mobility into a death sentence. The hedgerows of Normandy were not the neat garden borders planners had imagined. They were ancient earthen walls, thick with roots and vegetation, dividing the countryside into narrow corridors and kill zones. Tanks advancing through these lanes became trapped targets. German anti-tank guns waited in concealment, firing into the sides and rears of vehicles that had no room to maneuver. Within days, entire units were stalled, taking losses that threatened to halt the breakout from the beaches. Field commanders demanded a solution. What they received was not a factory design or a doctrine update, but improvisation from the crews trapped in the hedgerows themselves. American tank crews began welding scrap steel from German beach obstacles onto the fronts of Sherman tanks, creating jagged prongs that could tear through hedgerows instead of climbing over them. The devices looked crude and unbalanced. Engineers warned they would damage suspensions or destabilize the tanks. Crews installed them anyway. The results were immediate. Tanks fitted with these improvised cutters punched straight through hedgerows at speed, emerging into open fields with guns already trained on enemy positions. German defenders who relied on the terrain for protection were suddenly flanked and overwhelmed before they could react. At the same time, specialized ram tanks entered service. These heavily armored vehicles were designed to smash through obstacles by brute force, absorbing punishment that would have destroyed standard tanks and clearing paths for the units behind them. Neither solution was elegant. Both were assembled under fire, using whatever materials were available. But together, they broke the stalemate in the hedgerows and restored momentum to the Allied advance. Sometimes the most effective engineering decision is knowing when to stop calculating and start welding. Number 9 takes us to the seas around Europe, where fast attack boats faced an enemy they were never designed to fight. German E-boats and Allied motor torpedo boats were built for speed and stealth, striking convoys and coastal targets before vanishing into darkness. As the war progressed, they increasingly found themselves hunted from the air. Standard naval anti-aircraft guns were too slow to track fast, low-flying planes. Crews needed something else. They needed overwhelming firepower delivered instantly. The solution was to strip weapons from damaged or obsolete aircraft and mount them directly onto the decks of fast attack boats. Heavy machine guns, automatic cannon, and even aircraft rockets were bolted onto vessels never intended to carry them. The boats became top-heavy, recoil stressed their hulls, and stability suffered. On paper, it should have been a disaster. In combat, it became a lifeline. When aircraft attacked at low altitude, crews opened fire with volumes of ordnance that turned the air into a wall of metal. Pilots who expected light resistance suddenly flew into streams of heavy machine gun fire and explosive shells. Attack runs broke off, aircraft were hit, and the boats survived. The practice spread quickly. British, American, and German crews all reached the same conclusion. Stability and doctrine mattered less than putting as much fire into the sky as possible. If the boat stayed afloat and the guns kept firing, everything else was secondary. By the end of the war, fast attack boats bristling with aircraft weapons were common in coastal waters. They were ugly, unbalanced, and violated every principle of naval design. But they kept their crews alive when aircraft came hunting. That alone justified their existence. Number 8 shifts to a different kind of mobility. On the Eastern Front, Soviet commanders faced an enemy that had spent years perfecting defensive positions. German artillery was accurate, well-placed, and protected by infantry and armor. Traditional counter-battery fire was too slow. By the time Soviet guns responded, German batteries had already displaced. The answer was not more precision, it was speed. Soviet engineers began mounting rocket artillery systems onto the backs of trucks. The Katyusha had already proven effective, but now the concept expanded. Heavier rockets, larger launchers, and faster vehicles turned artillery into a weapon of shock rather than accuracy. The improvisation was crude. Truck suspensions were never designed to absorb the forces generated by rocket salvos. Launch frames were welded directly to chassis. Aiming systems were basic, often little more than alignment marks. Accuracy was poor by any conventional standard. But accuracy was never the point. When a Katyusha battery fired, it unleashed a storm of rockets in seconds, saturating entire grid squares with high explosives. German troops called it Stalin's organ because the rows of launch tubes resembled organ pipes, and the sound of incoming rockets announced devastation before impact. The trucks fired and immediately moved. Before German counter-battery systems could respond, the launchers were already miles away, reloading for the next strike. Firepower and mobility replaced precision and endurance. Other nations copied the concept. American forces mounted rocket systems on half-tracks and trucks. German crews improvised similar weapons using captured vehicles and salvaged launch rails. Everyone reached the same conclusion: mobility and volume of fire mattered more than accuracy. By the end of the war, truck-mounted rocket artillery had become a standard feature of mobile warfare. It was born from desperation, refined in combat, and proven effective by a simple measure. Crews lived long enough to fire again. Number 7 takes us into terrain where tanks became coffins. In the Pacific, across North Africa, and in the shattered cities of Europe, infantry needed close fire support against fortified positions. Standard tanks could not provide it. Their main guns were built to penetrate armor, not clear bunkers. Machine guns lacked the sustained effect needed to suppress defenders. What infantry needed was fire. Sustained, directed fire that could reach positions no shell could reliably destroy. The solution was to turn tanks into flamethrowers. Improvised flamethrower tanks appeared in every major theater. Crews removed main guns, installed internal fuel tanks filled with thickened gasoline, and mounted projectors capable of launching flame over long distances. The conversions were dangerous. Fuel tanks were vulnerable. A single penetrating hit could turn the vehicle into an inferno. Any rational risk assessment would have rejected the idea. Crews volunteered anyway. When a flamethrower tank advanced on a fortified position, defenders faced a brutal choice: surrender or burn. Pillboxes that resisted artillery were consumed in seconds. Bunkers collapsed as fire stripped oxygen from enclosed spaces. The psychological effect was often decisive before the flames even reached their targets. The weapons were not invulnerable. Flamethrower tanks carried limited fuel, usually enough for only a handful of sustained bursts. They were slow, obvious targets, and enemy forces quickly learned to prioritize them. Crews operated knowing each engagement could be their last. Despite the risks, flamethrower tanks proved indispensable. American forces used them extensively across Pacific Islands. British and Canadian units deployed them in European cities. Soviet crews improvised their own versions from damaged tanks and salvaged equipment. It was a weapon born from the brutal reality that some positions could not be taken any other way. It worked, and in war, that was the only standard that mattered. At this point, I'm curious, which invention so far surprised you the most? You can let me know in the comments while we move into the final half of the countdown. Number 6 brings us to the mind of one man who understood that battlefield innovation required more than individual improvisation. It required coordinated, specialized vehicles built to solve problems that standard tanks simply could not. Major General Percy Hobart commanded British armored units, and he saw what others overlooked. Beaches fortified with obstacles, minefields that stopped advances cold, rivers that could not be crossed under fire, defensive positions that ordinary armor could not breach. Each obstacle demanded its own solution. What emerged was a collection of vehicles so strange they looked more like experiments than weapons. They became known as Hobart's funnies, a nickname that disguised just how deadly they would prove. There were flail tanks that beat the ground ahead of them with spinning chains, detonating mines before the vehicle reached them. Bridge layer tanks carried entire spans and dropped them into place in seconds. Tanks equipped with fascines, massive bundles of logs, could be dumped into ditches to create instant crossings. Armored vehicles were fitted with searchlights powerful enough to blind defenders at night. Critics dismissed the machines as absurd. Hobart's vehicles were heavy, slow, and so specialized that they seemed useless outside narrow conditions. On paper, they violated nearly every principle of armored warfare. In combat, they saved lives. Flail tanks carved safe lanes through minefields while infantry followed close behind. Bridge layers kept armored advances moving when demolitions would have caused deadly delays. Fascine carriers turned obstacles into roadways. Each vehicle solved a problem that would otherwise have cost days of time and hundreds of casualties. Other armies had nothing comparable. American forces landing on Omaha Beach without specialized armor suffered devastating losses crossing obstacles that British units bypassed with relative speed. Hobart's funnies were not elegant. They were purpose-built answers to specific deadly problems. And when it mattered most, they worked exactly as intended. Number 5 moves beneath the surface of the Atlantic, where German U-boats were sinking Allied convoys faster than ships could be replaced. Submarine warfare had become a slaughter. Escort ships could locate submarines using sonar, but attacking them required sailing directly over the target and dropping depth charges almost blindly. By the time a ship reached that position, the submarine had often slipped away or dived too deep to hit. Convoys continued to bleed men and cargo into the ocean, and no existing weapon could reliably stop it. The solution came from a radical shift in thinking. Instead of chasing submarines, destroy them from a distance. The Hedgehog anti-submarine mortar fired a spread of small projectiles forward ahead of the attacking ship. Unlike depth charges, these weapons detonated only on contact with a solid object. If they missed, there was no explosion. If they hit a submarine, the result was immediate and lethal. Early trials were unimpressive. The system was complex. Trajectories were difficult to judge. Crews struggled to aim it accurately. Many doubted it would ever be practical. But tactics improved, and results followed. Submarines that could evade depth charges had no defense against a forward-thrown pattern. The contact fuses meant near misses gave no warning. Either the submarine was struck and destroyed, or it escaped completely. There was no middle ground. Convoys equipped with Hedgehog systems began sinking U-boats at rates that forced German commanders to rethink their entire submarine campaign. The weapon did not end undersea warfare, but it shifted the balance enough for convoys to survive the crossing. Hedgehog was never famous. It lacked spectacle, but for the sailors aboard merchant ships and escorts, it meant the difference between reaching port and dying in the freezing Atlantic. That alone made it one of the most important inventions of the war. Number 4 descends into a category of weapons so desperate they required men to carry the attack directly to the enemy. By the later years of the war, navies on all sides faced a problem conventional weapons could not solve. Harbors were heavily defended. Ships anchored in protected waters could not be reached by torpedoes launched from submarines or aircraft. New methods were required. The answer was human torpedoes. These were not suicide weapons in the conventional sense. They were manned underwater craft, slow and unstable, ridden by operators who guided them toward the target before attempting to detach the warhead and escape. In theory, the crews survived. In reality, survival depended on skill, luck, and whether the enemy noticed them in time. Italian naval commandos pioneered the concept, using two-man torpedoes to infiltrate Allied harbors and attach limpet mines to the hulls of warships. British forces soon adopted similar methods, developing their own craft for operations against German and Japanese targets. The missions were suicide in all but name. Operators rode exposed on the torpedo, breathing through primitive rebreathers, navigating by compass in total darkness. If the machinery failed, they drowned. If they were detected, they were shot or depth-charged. If the warhead detonated prematurely, there was no escape. Despite the risks, the attacks succeeded. Italian operators crippled British battleships in Alexandria Harbor. British crews damaged German capital ships in heavily defended anchorages. Japanese Kaiten, true suicide torpedoes, later struck American vessels in the Pacific. Human torpedoes were never a preferred solution. They were used when no other method could reach the target. They worked because men were willing to accept risks that machinery alone could not overcome. It was desperation made human. And it proved that no harbor, no matter how well defended, was ever completely safe. Number 3 takes us into the skies over Europe, where Allied bomber crews faced an enemy they could not see, predict, or evade. German radar-directed flak and night fighters were cutting bomber formations apart. Losses climbed toward unsustainable levels. Crews knew that every mission might be their last. The problem was radar. German detection systems tracked bombers from miles away, guiding fighters and anti-aircraft fire with deadly accuracy. The night sky became a controlled killing zone. Attempts to jam the signals failed. German operators adapted faster than countermeasures could be developed. What was needed was a way to blind the radar without transmitting anything at all. The solution was disarmingly simple. Thin strips of aluminum, cut to precise lengths, were dropped by the thousands from bomber formations. In British service, it was called window. In American use, it was called chaff. Each strip reflected radar waves, just like an aircraft. When released, the metal clouds filled enemy radar screens with thousands of false targets, overwhelming operators and collapsing the entire system. The first major use came during the bombing of Hamburg in July 1943. German controllers watched their screens dissolve into chaos. Night fighters lost contact with the bomber stream. Anti-aircraft batteries fired blindly. The bombers passed through with losses far below expectations. German defenses adapted within weeks, developing new frequencies and tactics. But Allied forces adapted faster, adjusting strip lengths and deployment patterns to counter every response. The idea spread beyond bombers. Naval vessels used chaff to confuse guidance systems. Ground forces used it to mask movements. The principle remained the same. Overwhelm the enemy's ability to see by giving them too much to see. It was not a technological revolution. It was a change in thinking. And in the skies over Europe, that change saved thousands of lives. Number 2 introduces a weapon that fundamentally redefined what artillery could achieve. For centuries, shells were blunt instruments. They followed predictable arcs, detonated on impact or by timed fuses, and hit whatever happened to be nearby. Against aircraft, success depended on guessing where a target might be seconds in the future. The odds were terrible. Thousands of shells were fired for every hit. Bomber formations took losses, but not enough to stop them. Anti-aircraft fire was a game of probability, and probability favored the attacker. What was needed was a shell that could decide for itself when to explode. The proximity fuse made that possible. A miniature radar unit was built into the nose of each shell, small enough to survive the violent acceleration of firing and rugged enough to function in flight. As the shell approached its target, the radar detected a reflected signal and triggered detonation at the precise moment for maximum effect. The technology was developed under extreme secrecy. If the enemy recovered an intact fuse and reverse-engineered it, the advantage would disappear overnight. Early shells were used only over water, where unexploded rounds were unlikely to be recovered. Duds were hunted down and destroyed. When proximity-fused shells entered combat, the change was immediate. Anti-aircraft fire became brutally effective. Japanese kamikaze aircraft were destroyed before reaching their targets. German flying bombs were knocked from the sky in numbers that rendered them ineffective. The impact went far beyond air defense. Proximity fuses were adapted for ground artillery, detonating shells above enemy positions instead of on impact. Defenders were showered with fragments they could not hide from. Entire assaults collapsed under fire that turned the air itself into a weapon. By the end of the war, the proximity fuse was one of the most closely guarded secrets in the Allied arsenal. It did not win the war on its own, but it transformed offensive fire from a gamble into a calculated kill zone. It was desperation refined into precision, and it worked. Number 1 is the most ambitious, desperate, and improbable invention of the entire war. An engineering project so vast that failure would have doomed the liberation of Europe, and success required building something no one had ever attempted. When Allied planners prepared for the invasion of Normandy, they faced a problem that could not be ignored. To land hundreds of thousands of troops, thousands of vehicles, and millions of tons of supplies, they needed functioning ports. Every major port along the French coast was heavily fortified, defended by elite German units, and rigged for demolition. Capturing a port would take weeks or months. The invasion could not wait. And even if a port was taken intact, it would likely be unusable. The solution was simple in concept and impossible in execution. If ports could not be captured, they would be built in the ocean. Mulberry harbors were artificial ports designed to be constructed in Britain, towed across the English Channel in sections, and assembled off the beaches of Normandy. Each harbor consisted of massive concrete caissons forming breakwaters, floating piers that rose and fell with the tide, and roadways linking the beach to deep water. The scale defied precedent. Millions of tons of concrete and steel were required. Individual caissons weighed thousands of tons and had to be towed across open sea without sinking. Engineers designed piers that could flex with waves while supporting tanks and heavy vehicles. Everything had to survive tides, storms, and enemy action. Critics called the project madness. It consumed resources that could have produced warships or aircraft. It demanded coordination across shipyards, factories, and construction crews on a scale never attempted. And if it failed, the invasion would fail with it. Construction was carried out in secrecy. Caissons were built in dry docks across Britain, then flooded to conceal them from enemy reconnaissance. Components were tested, refined, and staged without most workers ever knowing their final purpose. On D-Day, the sections were towed across the Channel. Within days, the first Mulberry Harbor was operational. Supplies began flowing onto the beaches at rates that exceeded even the planners' expectations. A violent storm struck 2 weeks later, destroying one harbor and badly damaging the other. Yet the surviving installation continued operating, moving more cargo than a natural port could have managed under the same conditions. By the time the Allies captured Cherbourg, Mulberry harbors had already delivered millions of men, hundreds of thousands of vehicles, and millions of tons of supplies, Without them, the invasion would have stalled on the beaches. With them, the advance into Europe became unstoppable. Mulberry harbors were not weapons in the traditional sense. They did not fire shells or drop bombs, but they made every victory that followed possible. They turned an impossible logistics problem into a solved one, and they remain the most desperate, most successful invention of the Second World War. If you stayed all the way to the end, you clearly appreciate the deeper side of history. If that is the case, subscribing ensures you do not miss future videos like this. If you would like to hear more stories about how real wars were shaped by real decisions, feel free to explore the channel.